What's up, everyone? Welcome back to Math 18A College Algebra. I hope you all enjoyed your spring break to the best of your ability. I've become almost completely nocturnal now. It's like 2:30 and it still feels like morning for me. But nevertheless, this week we're going to be finishing Chapter 3 and then starting Chapter 4. So today we're going to be doing 3.4. So without further ado, let's get into it. Alrighty, so hopefully you'll remember from a week or two ago, we've been studying these polynomial functions of higher degree, so like higher than quadratics, and we've seen that factoring these polynomials can be pretty tricky, so we wanted to avoid that. And we learned techniques like polynomial division and synthetic division to kind of avoid factoring. And so today we're going to be building on that idea by introducing a way to find factors and just apply our division algorithms. So let's start with the rational zero test, and that says that given a polynomial with integer coefficients, and remember that integers are just whole numbers, and they can be positive or negative, so not like fractions here, whole numbers. Plus or minus for the sign. So given a polynomial with integer coefficients, f of x equals an x to the n plus an minus 1 x to the n minus 1 plus all of your terms up until the lower ones, a2x squared plus a1x plus a0, this constant term. We can say that every rational zero has the form p over q, where p is a factor of this a0, and q is a factor of the leading coefficient, a sub n. And so you want to look at both of these, this a0 and this an, and list out the factors. So like look at a0 and an. List their factors. And then your 0 has to be of the form p over q, where we said that p is one of these factors of a0 that we can list out, and q is one of the factors of this an that we can list out. And then, so once you've listed those, you just try each one, essentially. Try the combinations. And I'll show you what I mean by that with an example. So let's say that we're asked to find the rational zeros of f of x equals x cubed plus x plus 2. So we see this polynomial here, and we don't see an easy way to factor it. So what do we do now? Well, let's try our rational zeros test. And so what I want to do is look at my constant term here. This is my a naught, or a sub 0 in this case. And look at my leading coefficient, a sub n, which is a sub 3 here, because we're of degree 3. And list the factors of those. So a0 equals 2. So the factors of 2, just like we've done with factoring in the past, we list our factors. The factors of 2 are 2 and 1, or negative 2, negative 1, right? And let's do the same thing for our a sub n, which is a sub 3 here. So a sub 3. Well, my leading coefficient here is just 1. So that makes it pretty easy for us. Well, factors of 1, all you have is 1 or negative 1, essentially, right? And so now I want to look at my p over q's, where p was a factor of this a sub 0 and q is a factor of this a sub 3. So let's look at all of our factors of a sub 0, which I have listed right here. So then for p over q, I can have 2, we'll just take this first one first, 2 over 1, or I can have 2 over negative 1, right? One factor of a sub 0 and then over the different possibilities of q. Or I could have 1 over 1, I can have 1 over negative 1, I can have this negative 2 over 1, or negative 2 over negative 1, or finally I could have negative 1 over 1, negative 1 over negative 1. And so if we simplify these, you'll notice that you get a lot of repeats, and that's good. You only have to check each one once, right? So if I reduce these, this one's 2, this one's negative 2, right? 2 divided by negative 1 becomes negative 2. I have 1 here, I have negative 1 here, and then this one will give me negative 2 again, so I have that already. This one will give me positive 2, because negative and negative makes positive, so I don't have to list that one again. And then the same for these ones, I already have these listed, because this one becomes negative 1, this one becomes positive 1. So these are all the unique p over q's that I have. And so now, all I have to do is test these in my original f of x and see which ones give me 0. So let's test these out next. Test p over q's in f of x. And so let's go to another page. My f of x was x cubed plus x, right? Yeah, plus x and then plus 2. And so our zeros, our p over q's were, or our possible zeros, p over q's were 2, negative 2, 1, and negative 1. So let's first try 2. It turned out ugly, there we go. Okay, so let's try 2. F of 2 is going to give me 2 cubed plus 2 plus 2. Well, these are all going to be positive, right? This is 8 plus 2 plus 2, so there's no way that that's going to give me 0. That gives me 12, right? So this one is not a 0. So 2 is not a 0 of this function. Let's try negative 2. So f of negative 2 equals negative 2 cubed plus negative 2 plus 2. Right, so negative 2 to the third is still negative, so it's negative 8 here. Negative 8 plus a negative 2, so that's minus 2, and then plus 2. So that's going to give me negative 8. So again, not a 0 of our f of x. So let's try 1. F of 1 equals 1 cubed plus 1 plus 2 equals 1 plus 1 plus 2. So that gives me 4. Again, not equal to 0. And then finally, let's try our last one. Try negative 1. So f of negative 1. Negative 1 cubed plus negative 1 plus 2 is going to give me negative 1 minus 1 plus 2. So this one does give me 0. So I found one of my zeros here. And I've tried all of the possibilities, so that means that that's actually the only zero that I have. Zeros of f of x. The only one is x equals -1. And remember here that saying that x equals -1 is a zero of f of x is the same as saying that this x minus -1 or x plus 1 is a factor of f of x. And so since we have that information, why don't we use polynomial division or synthetic division to factor this out of our polynomial? And I'll do both just to show you guys how that works. So let's first do polynomial division. Because remember, this is the one that you have to know how to do. Polynomial division for the final. Let's do x plus 1 on the outside, and then our f of x here, x cubed plus x plus 2. Oh, right, and I want to write out all of the terms, right? So I'm missing that x squared term. I should put a 0 for that, plus x plus 2. Okay, so x cubed plus x plus 2 divided by x plus 1. So two terms here. Why don't we look at our first two terms here? So I'll cut it off like this. And I want to look at, what do I multiply x by to get x cubed, right? Remember how we look at like the leading terms on both of these? And that's how I know what I need to multiply by. So I need to multiply this x by x squared if I want to get to x cubed. So I put my x squared on top here. And then I do the multiplication. So let's see, do multiplication. So I do x squared times my factor, x plus 1, which is going to give me x cubed plus x squared. And I want to subtract that. So x cubed plus x squared, this whole thing, subtracting it. And so we see that our x cubes cancel out here. And I have 0 x squared minus 1 x squared. So that's going to give me minus 1 x squared, or just minus x squared. Okay, let's move to the next term. We bring down this plus x, scooching our bar over a bit now. What do I want to multiply this x by to get to negative x squared? So you essentially just continue the algorithm. You can see that you need to multiply your x by a negative x to get to minus x squared, right? And we have to do our multiplication again. So we're doing negative x times this x plus 1. I guess I'll write it out over here. So we need to multiply by negative x. So we do that. Make sure you distribute everything. So negative x squared minus x is what I get from multiplying this out. And I'm subtracting that. So minus negative x squared minus x, which can get a little bit tricky with all the minus signs. So just make sure you're careful when you're doing this part. So negative and negative becomes positive x squared, so they cancel out here, which is what we wanted. And then negative and negative makes plus x. So I have positive x, so that's going to give me plus 2x. Right, I'm going a little bit faster this time because we covered polynomial division last section, so if you need to go a little bit slower, you can feel free to pause the video and try it yourself. But I'm going to continue. So bring down this plus 2. And now I want to see what I need to multiply my factor by to get to this 2x. So I already have x, but I'm missing the 2. So all I need now is a plus 2. And I do that multiplication. Need plus 2. And distributing that, 2 times x plus 1 equals 2x plus 2. So I'm subtracting that, 2x plus 2. And you can see that you just have this minus the same thing, right? So that has to be 0. And that's what we wanted, because we said that this x plus 1 was a factor, so it should give us 0 if we divide it out. There shouldn't be a remainder. So we can now write our f of x in factored form. So we factored out this x plus 1. And we're left with this x squared minus x plus 2. Okay, and I said that I do synthetic division on this one too, but I think I'll just skip that on this problem and do it on a different example. I don't want to spend too much time just doing one example. So let's take a look at this example. It's from a past final. So we let f of x equal x cubed minus 5x squared plus 2x plus 8. And we want to find the rational zeros of f of x by factoring f of x completely. And make sure that you include both the complete list of zeros and the factorization of f of x in your answer, which is what we did in the last one. So first we're going to find all the zeros, so we try them all, figure out what they are, and then we write f of x in factored form. So let's go ahead and do that. Okay, so first, using the rational zeros test, we look at this a sub 0, the constant term, which is 8 here, and the leading coefficient term, so just 1 again here, and we list the factors of those. So a0 equals 8, and so the factors of 8 are, you could have 1 and 8, you could have 2 and 4, and you could have all of the negative versions of those. Oops, negative, I'll do it in order. Negative 1, negative 8, negative 2, negative 4. And then again, we just have 1 for our a sub n, which is again a sub 3 here, because I'm degree 3. So I'm just going to have 1 and negative 1. And because I do all of the negative ones here, I actually don't even need to worry about this negative 1. Because, as you saw in the last example, you get repeats that way. And so taking the negatives of just one of, like this a sub 0 instead of both of these, a0 and a3, will give you all of the roots that you need. So next, let's look at p over q. So all of the possible combinations of these factors. And so we actually have quite a few here, but fortunately we're only dividing by 1. So all of our p over q's will just be like 1 over 1, 8 over 1, 2 over 1, oops, 2 over 1, 4 over 1, and all of the negative versions of those too. So negative 1 over 1, negative 8 over 1, negative 2 over 1, and negative 4 over 1. And so simplifying those, you just get 1, 8, 2, 4, negative 1, say it again, negative 1, negative 8, negative 2, and negative 4. So they're actually just exactly the same as these factors of p, or sorry, factors of a sub 0, all of our p's. And so if you have a leading coefficient of 1, then you just have to check these ones, essentially. So now that I have all of those listed, we want to test some of these values into our f of x. And let's go ahead. There's kind of a lot to check here, but you only need to find one that works, and then divide it out, and then you'll have a quadratic, and we know how to solve quadratics. So you can either plug all of these in to find the factorization, or you can divide. So why don't we just start trying them out? So f of x, let me copy our polynomial over, x cubed minus 5x squared plus 2x. And then plus 8. Okay. And so I always like to try the easy ones first. Let's just try 1. Because maybe you'll get lucky. Maybe 1 is 1, and then we can just divide it out, and we're golden. So f of 1 equals 1 cubed minus 5 times 1 squared plus 2 times 1 plus 8. So that's going to give me 1 minus 5 plus 2 plus 8. So it's looking like this one is not going to give me 0. Because I have 1 minus 5, that's negative 4, plus 2, negative 2, plus 8, that's going to give me positive 6. So this one is not a 0. Okay, let's move to a different one. Why don't we try negative 1? So f of negative 1 will give me negative 1 cubed minus 5 times negative 1 squared plus 2 times negative 1 plus 8. And so simplifying that, negative 1 cubed is negative 1 minus 5 times negative 1 squared, that's still minus 5 because negative 1 squared is positive 1. And then I need minus 2 plus 8. Okay, negative 1 minus 5, negative 6. Negative 6 minus 2, negative 8. Negative 8 plus 8 is in fact 0. So we found one. So you could say that x, again, x minus negative 1, which is the same as x plus 1, is a factor of f of x. Okay, and so like I said earlier, you could continue to test all of your possible zeros, and once you've tested all of them, you know which ones are zeros, or you can divide this factor out. And that's the method that I'm going to do for this example, but worst comes to worst, like you can always try all of them and see, like you can figure out all the zeros that way and you can write the factored polynomial. But let's go ahead and do synthetic division on this example. And remember, you can only do synthetic division when you have linear factors. So we have a linear factor here, this x plus 1. You can't do it if you have like x squared plus something, x cubed plus something. Has to be linear like this. So if you're finding zeros like we did here, then you'll always have a linear one, so that's really nice. Okay, so with synthetic division, we have to write our 0 on the outside, so negative 1 is going to go on the outside here. and then I draw this bar thing, and then here go the coefficients of my polynomial, and I don't have to put any zeros this time because I have a term for each degree. So I just have to copy the coefficients, and I take the sign with me too. So 1, -5, 2, and 8. 1, -5, 2, and 8. Okay, and let's remember our synthetic division algorithm. First we go downward. Bringing this 1 down just gives us 1. And then going diagonally, we have to multiply. So -1 times 1 is going to give me -1. Going downwards, I have to add. So -5 plus -1 is going to give me a -6. Going diagonally again, you have to multiply. So -1 times -6 is going to become +6. Going downward, we're adding. 2 plus 6 is going to give me 8. Finally, going up and to the right again, diagonally, I'm multiplying this -1 times 8, so -8. And the last entry going downward, that's going to be adding 8 and -8 is going to be 0. And again, that's what we wanted. This is our remainder. And we want remainder 0 because it's supposed to divide evenly. So what that gives me is I had this factor x plus 1, right? So factored polynomial. We have our first step here. So we had this x plus 1 was a factor, which is the same as saying that -1 is a 0. And then this, these numbers here determine the coefficients of my new polynomial here. So 1 x squared minus 6x plus 8. And remember, the degree has to go down. This original one was cubic, and I pulled out one factor, so now this is a quadratic. So this is the first step. This isn't quite factored yet because we might be able to simplify this further. And looking at this, I can see that this should factor, but it might not be as clear to everyone, so you can always do your discriminant test to see if it does. Which is b squared minus 4ac, so -6 squared minus 4ac, which is 1 and 8. So -6 squared is going to be positive 36, minus 4 times 1 times 8 is 32. So this is 4, positive 4, right? Greater than 0. That means that I do have two real solutions. So two real solutions to this quadratic here. So you can either factor it or you can use the quadratic formula to find the other zeros. But I will just factor it. So this isn't quite the factored polynomial yet. This is just the first step. But we just need to take it one step further. We had this x plus 1. And now I want to factor this quadratic. So I'm going to set up two bubbles here. I'm looking at factors of 8 that sum to -6. And so factors of 8, well, I can see 4 and 2 would make sense here because those are going to sum to 6. And then I just need to make sure that they have the negative ones, -4 and -2, right? -4 times -2 will multiply to 8, positive 8. and then we'll sum to -4. So I just need to put those in here. And so if you did the quadratic formula on this instead, that would work fine too. You just wouldn't end up in factored form. It would give you the zeros explicitly. So let me do that real quick too. X equals -b plus or minus the square root of b squared minus 4ac over 2a, the whole thing over 2a. So here that's going to be -6 plus or minus square root of b squared, -6 squared, minus 4ac over 2a. So -6 becomes +6 plus or minus, this was b squared minus 4ac, which I already calculated for my discriminant. So that's going to reduce to 4. So square root of 4 over 2, which is going to give me 6 plus or minus, remember that square root of 4 is 2, over 2. This splits into two different solutions here. 6 plus 2 over 2 and 6 minus 2 over 2. This one will be 6 plus 2 is 8 over 2 is 4. And 6 minus 2, 4 over 2 is 2, which is what happened when we factor this. So then if you did this method, you would just have to write these as factors instead. So like write these so this one is x minus 4, this one is x minus 2. Okay, so let's just finalize the answer to the question. It asked us to find the rational zeros of f of x by factoring, and we're supposed to put a complete list of the zeros and the factored version of f of x. So I would just write the zeros are the one that we found originally, which was -1, right? So we had -1. We then solved this quadratic to find the two other ones, and the two other ones ended up being +4, +2, which we also saw here, 4 and 2. And we have all three of them here. Because we started with a cubic, an x to the third power, we can have at most 3 real zeros, so you can't have more than 3. And we found 3, so that means that we're done. And then we just have to write the factorization. Which we did on this other page here. F of x equals x plus 1 and you actually just get that from your zeros. So x plus 1, x minus 4, and x minus 2. So the zeros list and the factorization of f of x. Okay, and then I do quickly want to do an example of one that doesn't have a leading coefficient of 1, so that you'll have to actually check this a sub n. So let's quickly do that. A sub 0 here is -2. So if I'm listing the factors of that, you can have like -1 and 2, or you can have 1 and -2. And then a sub 3, again here, they're all cubic. It obviously won't always be cubic, but cubic is kind of a good example. So a3 equals 2. So if I'm looking at factors, and remember I covered the negative ones up here, so I'll only do positive ones down here. So all I need to worry about is 1 and 2. Okay, so then if I'm listing my p over q's, I can have negative 1 over 1, negative 1 over 2, 2 over 1, 2 over 2, and then 1 over 1, 1 over 2, negative 2 over 1, negative 2 over 2. And we might even get more repeats. It's looking like we will end up with it because some of these will reduce to the same thing. So reducing them, I get negative 1, I get negative a half, 2, 1. This one also gives me 1. This one will give me positive 1 half. This will give me my negative 2. And then this one will also give me negative 1. So I have those covered already. So this should be a complete list of all of the zeros that I need to check. So let's go ahead and start trying them. And if you just kind of look at this, you can sort of guess what might give you a 0. Like look, if I plug in 1, well then I just have 2 minus 2, so that one should give me a 0. So let's try 1. F of 1 is 2 times 1 cubed minus 2, which will give me 2 minus 2 gives me 0. So 1 is a 0, which means that one of my factors is x minus 1. I will do, since you often don't want to like just extensively or exhaustively try this list, like plug them into the function, because sometimes you'll have fractions and those aren't typically very fun to plug in. So I always just end up doing synthetic division. I found that 1 was a factor, so I write 1 on the outside. I take my coefficients and I'm missing an x squared term and an x term. So I do need to write zeros in this case. So 2 for the x cubed, 0x squared, 0x, and negative 2 for my constant term here. Proceeding with the algorithm, bring down that 2, multiply. 1 times 2 gives me 2. If I'm going down, I add, so 0 plus 2 is 2 again. Doing multiplication, 1 times 2 is 2. Addition, 0 plus 2 is 2. A lot of 2's here. And then finally, 1 times 2 gives me 2 one more time, and then 0 remainder. So then I have a quadratic now. I reduced the order of this function by 1. So I now have x minus 1, and I have 2x squared plus 2x plus 2. Let's see if we can reduce this further by doing the discriminant test. So b squared minus 4ac. Here that will give me 2 squared minus 4 times 2 times 2. So 4 minus 4 times 2 is going to be 16. So that's negative 12, which is less than 0, which means no real solutions to that quadratic. So this is actually the factored form of my f of x, and I found all of the rational zeros just by testing this 1 here. So all of the real zeros, it was just x equals 1. And then factored form, f of x equals x minus 1 times 2x squared plus 2x plus 2. Okay, and then the last thing that I want to leave you guys with is this theorem called the intermediate value theorem, which if you're going on to business calculus, you will almost certainly see this. And it says that let a and b be real numbers such that a is less than b. If for a polynomial f we have f of a is not equal to f of b, then on the interval a to b, if f takes on every value between f of a and f of b. So that doesn't make a lot of sense right now, just in words, but let me draw you a picture. Oopsie. So let's say, and it actually doesn't have to be a polynomial f, it just has to be a continuous function f, but let's draw some kind of a polynomial like that. And let's say that a is here and b is here. And then that means that f of a is this number, like on the graph, it's f evaluated at a, and f of b is this, where this function here is my f of x. And so we have here that you can see that f of a is not equal to f of b. F of b is lower, right? F of b is less than f of a. And since our function f is continuous, like it has no breaks in it, remember we talked about that, all this says is that f takes on every value between f of a and f of b. So there's always going to be, like, say that this is some value between f of a and f of b. There's going to be some x value where that happens. And this is useful in this chapter specifically because if you're looking for zeros, let's say you have some polynomial that looks like this, and maybe you made a sign chart like x and f of x, and let's say that we found for some value of x, like over here we'll call this 1. Let's say that at x equals 1, your f of x was also 1. And let's say that over here at x equals 3, your f of x was like -2 or something. These are completely made up also. So let's say that this is the scenario we're in. If you see that this one is positive and this one is negative, so I have two different values of f of x, and one is above the x-axis, one is below the x-axis, there has to be a place where f of x was 0 between these two x values. So it's really just thinking about it like in terms of the picture. If I know that I have a positive value and then a negative value, and I have a polynomial function which has to be continuous, that means that there is a 0 in between these x values that I have. So by intermediate value theorem, there must be a 0 between x equals 1 and x equals 3. So that's just something to keep in mind, like for calculus, or if you ever find yourself in a situation like this. I don't know if you would, but this is a good theorem to know.